Final video on this topic is measuring value at risk for an options portfolio. So previously we've talked about the mitigation of risk. For equity portfolios, diversification is the key. For options portfolios, the delta gamma vega hedging is that's a very important part of the risk management process. But for every type of portfolio we look at, we are also considering how to measure risk. And eventually we're getting to that at the very end of this topic. So this is where we are at last, measuring value at risk for an options portfolio. And for that, we are going to need that Taylor expansion stuff that we did at the very end of the maths video. And here it is. There's a Taylor expansion immediately on this first slide. This is 0.5. So I'm writing it in a slightly different way to the way that I wrote the Taylor expansion. So let me show you here. First of all, I'm taking the fx0, this constant, to the other side, to the left-hand side, so that what we see is a change in this case, the option price. And I'm letting this be x and this be x plus a little bit. And then there are two variables. So I'll just show you here. I can go straight to it. So this is the f, like the f of x, only we've got two variables. Actually, this is where we start, and then this is the new one where we've got another point there. And x minus x0 is just hs, or h sigma. So you can think of the s plus hs as being the x and s as being x0. And so x minus x0 is hs, likewise for h sigma. And then you've got x minus x0 times the first derivative, that's the delta, and a half x minus x0 squared, so that's the hs squared, times the second derivative, which is the gamma, plus h sigma now, because it's the second variable, times the first derivative with respect to volatility, which is the vega. So this way, given whatever pricing model we've got, we're going to be using the Black-Scholes in the example, we can compute the delta, gamma, and vega, and then use this to approximate a new option price, or a new position price, actually, overall. If we use the position delta, gamma, vega, then we can find the approximation to the entire position. But in the example, I'm just going to keep it to one option, not a whole book of options. Now, because for at least short-term standard European options, S is by far the most important risk factor. Yes, volatility is an important risk factor, but we don't take a second term. We don't have a 0.5 H sigma squared gamma here. Because anyway, option prices are, at least if they're near at the money, they're pretty much linear functions anyway. So you don't need that second order quadratic approximation really on the volatility side of those things. But anyway, when it's short, and that means vega is small, vega is much bigger for longer options, then delta gamma approximations are quite common. And that's what we're going to use in our example. So numerical example first. Consider a 30-day out-of-money European call option with strike 105 on an asset that pays no dividends and no carry cost. Okay, so the Y is 0. Current asset price is 100, its volatility is 35%. The 30-day risk-free rate is 5%. We had this before in our previous example, but of course we can change anything in the Excel spreadsheet. Now suppose the asset price falls from 100 to 95, it's quite a big fall. About as big as you'd want with just a delta approximation. But now, if we're going to find a delta gamma approximation, yeah, that's quite important to add the gamma for such a big price fall. And the volatility increases from 35 to 37%. find the delta gamma approximation and the delta gamma vega approximation to the change in the option price. That's what you get. You get not a new option price. On the left, it's the change in the option price. So once you've estimated the change, you have to add that to the option price to get a new option price. So we know from previously these numbers, delta, gamma, and vega. And so we have -5 for quite a big fall. So it's the delta gamma approximation to the change in the option price, call it delta F for the change in the option price, is -5, that's the HS, times the delta, plus 1/2 times -5 squared, that's 25, times the gamma. So that's -1.27224. And then adding on another term for the vega, that gives us 2 for the H sigma times the vega, which is 0.10579. We can also look at the solution in the Excel file. So let me do that now. Here we are. So we've seen all this before, played around with this spreadsheet. Anything you want, you can change. This is blue. Can't change those. And I can't change any of these. Look, we've got all these formulae beneath them. Now, the delta gamma approximation takes the change in the underlying price, multiplies it by the delta, plus 1/2 the change in the underlying price squared, multiplies it by the gamma. And so that's the change in the option price, and the new option price is going to be the original price plus the change. And for the delta gamma vega here, we've got a different new option price. Now, it should be a little bit more accurate to use the delta gamma vega approximation. Why don't I just copy these and just keep an eye on them. Just going to paste them as values. Just the values there. Because what I'm going to do now is I'm going to look at this price here and see what is the actual price if I change this to 95. Is it 0.93464? That's the delta gamma approximation, or is it 0.14621? Sorry, yes, 1.142. What is it? What is it when it comes down there? And it's 0.90, actually closer to the delta gamma approximation. And with the change in the volatility for the vega, delta gamma vega, I'd also have to change the volatility to 37%. And yeah, so you can see that they're not particularly accurate for such large inputs. So remember that you add the change to the original price to get the approximation. Just putting this back as it is, because I want to save this spreadsheet. Now, finally, how do we find VaR? Well, normally we can't use the normal linear VaR model, remember, that's just for linear portfolios, and this isn't a linear portfolio, but we can use historical simulation, which is what most banks use. And that's why we use this delta gamma vega approximation. We find this portfolio's net position delta gamma and vega, and then we simulate the P&L, the change in the price for different historical values now for HS and H sigma. And we get a whole time series of historical changes in the underlying, say they're all, the portfolio is all options on S&P 500. So we just take the S&P 500 daily changes, and each one would be an HS, which we put in there. And on the same day, we'd have to take the change in implied volatility. and that is quite difficult to get. We probably use something like an at-the-money volatility or the VIX index, but I haven't really talked about implied volatility in this module. It's a little bit beyond the scope. So I'm just going to ignore that, and I'm only going to do a delta gamma demonstration. And once you've got your historical time series of P&L, we just use the percentile function in the usual way to get the VaR. So for example, you've got an S&P 500 options portfolio with a net position delta of minus 0.75 and a net position gamma of 0.3. Use 5 years of daily closing price data on the underlying to compute the 1% 10-day historical VaR using a delta gamma approximation for the changes in the portfolio value when the S&P index changes by HS, which is your delta T. There's no changes in implied volatility, just using the S as a risk factor. Solutions in the Excel workbook, which we'll then finish with now. Here we are. So here's our historical data on the S&P 500. These are the daily P&Ls, which we use for HS. Then using this delta and this gamma fixed, the delta gamma approximation has got dollar sign in front of $G, $1 and $G, $2, so they won't change, but what does change is your HS, which is in column C. And this is what the P&L look like here. And that gives us a time series of changes in the option price. And then for the value at risk, we just use the percentile on that, multiplied by the square root of time rule, and the percentile is at the required alpha. So couldn't really be easier, really. I think before I've called that the significance level, yeah? And I've also called this the holding period. Just to be consistent with previous sheets, I'll change those as well. Right, come to the end of this lecture, and only one more to go.